Then we'll move to our next speaker, Madeleine Yttergren. Madeleine, if you can start sharing your screen. Yes, thank you very much. So our next speaker will be Madeleine Yttergren. I hope I am pronouncing your family name correctly. She will try to answer the question, how well can we determine the kinematics of high redshift galaxies, ALMA, the effective resolution, and other important considerations. Please, Madeleine, go ahead.
Yeah, thank you. So thank you for the introduction and thank you for having me. Today I will tell you about this exciting project we have that we recently started that concerns how well we can determine the kinematics of high redshift galaxies. I want to begin by giving you a bit of a better feeling of how ALMA has affected our relationship to distant galaxies and the important effect of spatial resolution. Then we'll look at a couple of kinematical studies of galaxies and some important aspects that one needs to consider when studying galaxy kinematics. As you've seen in the previous talks in this conference, it's not completely straightforward. And thereafter, I will present the outline and current state of our project. How galaxies have evolved across the history of the universe is one of the big questions. I need to move you out of the way. And a common approach is to look at the star formation rate across cosmic time through the cosmic dawn and the cosmic noon, as plotted here and explained very nicely by Melanie yesterday. And what I want you to note is that in early time, the universe was awash with gas, and the close spacing between the galaxies lent itself to intense evolutionary activity, and a significant portion of the star formation activity was heavily enshrouded in dust. Understanding the prevalence and nature of the dusty star formation over the lifetime of the universe has remained a challenge. And before ALMA, telescopes such as Herschel contributed significantly to our understanding of the cosmic importance of dust obscured star formation, although the poor angular resolution led to significant source bleeding. So most of what we knew of distant galaxies was limited to the brightest sub-millimeter galaxies. But this information was sparse, and only the most extreme or strongly lensed galaxies could be resolved. In this figure here to your left, you see an image obtained with the La Boca camera on the Apex telescope, covering a size of the sky about the size of the moon. The galaxies seen by La Boca are marked in red here. And as you can see, they look primarily like red blobs spread over several tenths of arcseconds. And it's difficult to say anything about the details of the individual galaxies. Now, I would like you to focus on one of the red blobs and remember it while we go to the next slide. Each square in this image is smaller than the red blob you were looking at in the previous image, or comparable in size to if you picked a very small red blob. And the ALMA data here is colored in red. So here you can see that ALMA could pinpoint the centers of galaxies and separate them from each other. So instead of believing that we were seeing this extremely bright galaxies forming stars at 1,000 times more vigorously than our own galaxy, at the risk of blowing themselves apart, ALMA showed us that there are multiple smaller galaxies in this red blobs, forming stars at somewhat more reasonable rates. And the detail that we can obtain in distant galaxies with ALMA still doesn't look like much if you would compare it to, say, for example, ALMA data of nearby galaxies, but it is huge, and so many new interesting details continue to be revealed. But we are limited, particularly by the spatial resolution, simply due to the large distances to the high redshift galaxies. If you plot how the spatial extension of an object on the sky, your solid angle in kiloparsec per arcsecond, how it varies with redshift, you'd get a plot like this. And as you can see in nearby galaxies at, for example, a redshift of 0.002, we can observe around 43 parsec per arcsecond. So if we have a 1 arcsecond resolution, I would say that that's quite nice, and we can get quite a lot of structure in our data. But as we move to higher redshift, we quickly leave the sub-kiloparsec range and reach resolutions of 3, 6, 8 kiloparsec per arcsec. Then it does decrease again due to the expansion of the universe and the finite speed of light. But to illustrate what this actually means, I have this image here. This is NGC 4303 as imaged by ALMA and Muse. And this first image here, the left one, is at its actual redshift at 0.005. And you can see this beautiful structure in detail. And that's because we can see 100 parsec per arc second. But for illustrative purposes here, I have modified this here to show if you imagine that you observe this galaxy at a redshift of 0.05, where we have 1 kiloparsec per arc second, the galaxy would look this large in your field of view. Instead, if the galaxy was located at a redshift of 0.5, where we have 6 kiloparsec per arc second, it just looks like a dot. So yes, the resolution is incredible with ALMA, also in the ALMA observed high redshift galaxies, and we're seeing structures and details that we've never seen before. But that does not mean it's without limitations. So now we have gotten a bit of an idea of ALMA and the limitations of spatial resolution due to distance. So let's move on to look a bit at galaxy kinematics. And let's first look at the kinematics of a nearby galaxy in a complex evolutionary inducing environment. This is NGC 7319, or this galaxy. It's an active galaxy in the compact galaxy group Stephan's quintet. It has been involved with many of the interactions in the group in the past and present. But what I want you to focus on is the moment maps. So this is the optical spectroscopy data from the Large Binocular Telescope. And here you have the stellar continuum, flux line of sight velocity and velocity dispersion, and the O3 line. And as you can see, the spatial extent and the velocity fields of the star component and the O3 line are very close to perpendicular. It is actually possible that all of the gas observed in this galaxy is in the form of a large-scale nuclear wind. However, we need higher sensitivity data to be able to say for sure what's going on. And this is for a somewhat complex nearby galaxy. It's located at a redshift of 0.02. And our data spans around 20 times 20 arc seconds. Imagine instead that you're doing this kind of analysis on a distant galaxy, where the whole galaxy is encompassed within a couple of arc seconds, and it's likely in a more extreme evolutionary state. How can you then distinguish different kinematical structures? How can you separate alpha from rotation? Can you? In a pilot study by Thon et al., they observed 3 hot dust obscured galaxies with ALMA at a redshift of around 3. And I'd like to pull your attention to 3 spectra here. As you can see, there are some complexity to the velocity structures of the CU emission lines in these 3 galaxies. The authors suggest that in the case of the middle one and the right one, where we have these asymmetric lines, what we're looking at is likely molecular outflows, although gas-rich mergers could also explain these kind of structures. The left-hand galaxy is possibly a gas-rich merger, a 3-galaxy merger, but molecular outflow cannot be excluded. So sure, this is great and very interesting, but it doesn't make me feel very confident. But Schultz et al. Are working on this beautiful sample of 14 hot dogs, which include the galaxies observed by Thon et al. From my previous slide. And here you see an example of W0410. And these are the moment maps from the ALMA observations of this galaxy. And Schultz et al. Fitted this galaxy with a rotating disk using the kinematical tool GALPAC 3D. You see the model here. And this actually left a residual with a velocity gradient, as you can see here to your bottom right. So with this kind of 3D kinematical analysis, Schultz et al. Actually can lend weight to an alpha structure in W0410 as proposed by Thon et al. But you might note that the velocity gradients are somewhat similar in the rotation and outflow structures. So GALPAC 3D, as I just mentioned, the tool that Schultz et al. Used to fit W0410, it's one of several publicly available 3D kinematical tools for high redshift galaxies. 3D Barolo is another that was used in the works by Fernanda and Roberta presented earlier during this conference. CubeFit and Terrific are 2 other options. GALPAC and CubeFit utilizes a disk parametric model and MCMC, and you can see an example of the fitting with CubeFit to your right. 3D Barolo and Terrific, on the other hand, uses a tilted ring model, as you can see illustrated in the center of the slide. A common assumption for kinematical tools is that the galaxy fitted is a nicely rotating, thin axisymmetric disk without, there's no mergers, there's no outflows. And as you know, this is quite a stretch, which also Sander showed us in his talk the day before yesterday, and Melanie discussed with the importance of disk thickness. And Neeleman et al., who developed CubeFit, they studied the C plus emission in 27 quasars at a redshift of around 6, and found that a third had a velocity structure resembling a rotating disk. A third seemed dispersion dominated, and a third were disturbed, for example, mergers or companion galaxies. But if we assume that we have a nicely rotating disk, there's still a number of decisions that we have to make regarding the flux, rotation velocity, and velocity dispersion profiles. For illustrative purposes here, for you, I've plotted a selection of brightness profiles and rotation curves. And what I want you to note is that there's quite a spread. And the choices that you make have a physical meaning and an effect on your fitting conclusions. So you have to be aware of what the choices you're making. Another degree of complexity that I want to highlight concerns the shape of the line profile due to galaxy inclination. This plot here shows this beautiful simulated galaxy by Cohandle et al. So this galaxy evolves from a redshift of 6.48 to 6.28 to 6.18, where it goes from being classified as a merger to a spiral disk to a disturbed disk. And this left images here, they show the face on in these 3 stages, whereas the right show the edge on of the same structure at the same time. And to each side, you have the line profile in each case. So for example, for the merger, you see, if you look at it face on, you have this slight asymmetry in the line, but if you look at it edge on, you have a whole slew of stuff. So there's quite a difference in the line profile if you're looking on it edge on versus face on. And I can't help but wonder how we can determine or even constrain the inclination or morphology of the galaxy if we're seeing something like this with a several kiloparsec resolution.
3 more minutes.
To start sorting this out, we have devised a project. We begin by simulating a rotating disk as if it had been observed by ALMA at high redshift and run it through the kinematical tools. And we study the effect of the limited resolution and signal to noise on the ability of the tools to reproduce the simple structure. Then we add biconical outflows or inner disk rotating at a different velocity, and we run them through the tools as well. And we see how well these structures can be reproduced and how it affects the conclusions drawn. And then, depending on which collaborations and data we have, we'll use simulations of more complex systems or reduce the resolution and signal to noise of observations of nearby galaxies and run them through the tools to explore the reproducibility of these more complex structures and the effect of limited resolution and signal to noise on the conclusions that we draw of our data. If you're interested in collaborating on these parts, please contact me. Because we aim to understand the limitations of the resolution and signal to noise, of how well the current kinematical tools can reproduce the actual structures, separate alpha from mergers from rotation, and together with also my work by my colleague Asnikau, who works with gas excitation, we hope to reach an understanding of just how well we can constrain and distinguish kinematical structures in high redshift galaxies. So we started this project last year. And since then, we have written a simulation of a rotating disk and are working with the kinematical tools to ensure that the simple structure can be reproduced. This is the current state of the Fitwit Galpak. We still have some bugs and aspects to work out, but we can already see an interesting preliminary indication of the difficulty of the kinematical tools in correctly determining the inclination and rotation velocity simultaneously, with an underestimation of the inclination and an overestimation of the rotational velocity. And that brings us to the last slide of my talk. So ALMA has revealed structures and details in high redshift galaxies that we have not been able to see before, but we are limited by particularly the spatial resolution due to the large distances. 3D kinematical tools help us along the way to clarify the kinematics of these galaxies, but they are subjected to a large number of assumptions and choices. They generally assume that we have a simple rotating disk. So what will happen if you then have a galaxy with an outflow or a merger, or a galaxy going through an intense evolutionary change, which is often the case for high redshift galaxies? With the resolution we have, can we separate outflow from mergers, from rotation? How does the limited resolution affect the conclusions we can draw of our data? So, and this is what our new and ongoing project comes in. And we aim to explore and understand just how and how well we can determine the kinematics of high redshift galaxies. We want to understand and clarify what we need to consider and what conclusions we can draw based on what data when studying the kinematics of these distant high redshift galaxies. And then I'm done. Thank you for your attention.
Thank you very much, Madeleine, for bringing up this quite important point. Elisabeth, do we have any questions? I have one.
Yes, one appear now.
Okay.
You talk some fantastic work. How important is the disk inclination for accurate modeling?
A lot. As you can see in, hold on, I'm going to go back. As you can see here, you see how much the inclination affects. So this is just face on and edge on, right? And you can really see how the line profile changes depending on which direction you're looking at the galaxy in, but also in smaller inclinations. In the fitting that we're doing now, that I said we do have some bugs left to work out, but it has an issue with getting with underestimating the inclination. And when it underestimates the inclination, it has to increase the rotational velocity to compensate to get a rotating disk. So it's quite a difficult one to distinguish, because how do you also, so if you assume you have an exosymmetric galaxy and you assume you have as much gas everywhere, you can then assume that you have it's circular, right? So then you can fit the inclination based on the elliptical. Like, it's a very difficult question to answer, and it's something that we hope to get some kind of idea of how big of an effect it has.
We have more questions.
Yeah.
Thank you for an amazing talk. Can we use ALMA for studying the chemical evolution of high redshift galaxies using simulations?
I want both, right? I want observations and I want simulations so that we can, but then I guess I want to understand. You also, yes, of course, simulations are very important, very useful, but you also need observations to make sure that they are correct. But with the resolution and the limitations that we have on our observations, we have to know if we can make what we see, what we think we see. Generally, like if we have wings, we assume they're outflows. If we have other velocity gradients in our residuals, we assume they're outflows, but they might be minor mergers. We have to understand how we can translate these to each other. So how we can merge observations and simulations as well, and how well we can actually fully understand what's going on. Is that an answer?
I think so.
And otherwise we can continue that on the Slack. There's more questions, and we have some time.
A lot of questions are coming. Very important use for work. I was wondering whether you plan to add the lensing effect into your modeling to test whether we can recover the lensed kinematics.
No, that's not in the plan at the moment, but it would be very interesting to incorporate for the future. Thank you for that suggestion.
Maybe one short last question.
Have you had a chance to compare the different modeling tools yet? Do title models yield the same velocity dispersion as smooth profiles?
Sorry, can you say that again?
Have you had a chance to compare the different modeling tools yet? Do title models yield the same velocity dispersion as smooth profiles?
I have not. I have so far started with the CubeFit and the GalPack, which both use this parametric approach. But I'm looking forward to using 3D Pro and Terrific as well to see how. I expect there to be some differences.
Okay, thank you very much. There are some more questions, but if you have time, we'll copy them all to the Slack channel where you can take a look at them and answer them. Thank you very much for this wonderful talk.